my data set. So if you want to copy, you just have
the screen is blocked. We can't see anything.
Oh, please, can you see it? I just share my screen. Can you see that?
Yes, yes, we can.
Yes.
Yes.
Now, yes. Now, yes.
No?
Okay, that's
Yeah.
okay. Then let's go ahead. Let's go ahead. So the ones you've learned this, you then have to copy your data. So just click Control and A at the same time. Control A to highlight your data. You right click, then you click on copy.
Sir?
I hope you're following that.
Hello, Dr. Robert.
Yes.
I think when you copy your data, we are not.
I should show the screen. Okay.
Yeah,
I wanted to show the screen.
Yeah,
So
you
you
copy-
show the whole screen. Wait.
You copy from Excel, right?
Okay, that's
Copy-
okay. That's okay. I'll share that screen for you. Let me share
Or
all
maybe
my.
you can import the data like through the
Okay,
normal.
wait. Let me share my whole screen so that you can see anything that I'm doing.
Okay.
Yeah, I've done that. So now you can see. So what you do is that you just click Control A to copy. Then you right click, you copy this. Then you come back to STATA. What you do is that you go to the data editor, you copy, and you paste your data. So you click Paste Special. Then you click on that. You choose this. Treat first row as variable names. Then okay. You get that? Yeah. So.
Hello?
Yeah, hello. Are you with me?
Not really.
You're not seeing it?
Where did you get these data sets? Where did you get these data sets?
I've shared this data set with you. You guys have the data set. This data I'm using, I've shared them with you.
Please, the data set copied is on Excel file straight. Is there no need to convert to STATA format?
Hello, everyone.
No, you don't need to. You don't need to do that. Don't worry. Later, I'll welcome all your questions. But what I'm saying is that I've shared the data that I'm using with you.
Dr. Fiction,
Yes,
please
you did.
give me a minute. Hello, everyone. I shared the data sets to the WeChat groups. I also send them to the chat box. I will send them back to the chat box. Doctor is using the data 2, the second
data set.
He is not importing the data. He is doing it manually. You copy your data from Excel, go to data editor, and you paste. If you are not okay with that process, you can import yours through the normal file.
Yes, you can just do that.
Or wait, when he finishes the first session, then the questions will come. Let's have a flow, okay? We beg you.
Okay, so okay, now that we're done with this. So I've pasted my data now. So what I need to do now is that I first have to declare my data as time series. So the first step you do here, once you upload the data, import your data. And then after you have imported your data,
Excuse me, sir. Sorry, excuse me, sir.
I'm listening.
So please, which particular option did you use to paste this data on STATA? Because I didn't hear the audit. Yes.
Just go to data editor. You click on data editor, then you just paste your data there. You right click. When you right click, it will give you an option. You just select
raw or transform data.
It depends on what I want to do now. I have, okay, wait. Let's first come to let's use the raw data. Let's use the raw data so that after that, we'll come back to the transform data because I have a reason why I gave you these two data sets. So let's first use the raw data set, okay? Let's use the raw data set. We'll come back to use this one. Let's use this. Okay, you copy. Then you come back. Let me clear this. Up. Okay, done. So, like I said, you just click on, you right click, then you select paste special. Then you choose treat first row as variable names. Okay, so I have it pasted. We're using the raw data set. We use, damn it.
Hello?
Wait.
Hello?
Yes.
when you click
when you copy, don't include the country. When you're copying, don't include the country. Just select from years, okay? Just copy from years. Delete the country part. Delete the country parts from, if you have your data, when you open it, just delete the country part of it. Delete the country part of your data set. Can you hear me? I took this data from my work, so it's a panel work. So okay, I've deleted the country parts. Can you see that? Delete the country parts of the raw data set. Just delete the country where you see China, China, China. Delete that part. Okay.
Yeah, Doctor, we can hear you, but you are a little bit too faster. That's the truth.
Oh, okay. So I understand. What I'm saying is that with the raw data set, the first column, please delete the first column where I've written country and China, China, China stuff. I just got this data set out of one of my panel works. So delete the China where you have country, then under that you see China, China, China. That column should be deleted. So when you copy, just copy from the years and copy that part. Okay. So please delete the column where you have China, China out of your raw data set. Now let's move on. Let me come back. Like I said, I'm just repeating the process. Okay, so I go to editor, data editor, then I paste my data there. Okay,
Doctor, why do we paste it as a paste special, not just paste?
Oh, you go to the editor, data editor. You click on it. It will open a dialog for you. Once the dialog is open, the next thing you should do is that you right-click. Just right-click, and to give you there's something will pop up. That pop-up, just choose treat the first row as a variable name. Select that one.
First row
as a variable name. Once you do that, then you click OK. Are you done? If you're done, then let's move on. Okay, so like I said, once you import your data, what you have to do is that you have to declare your data set. You just have to declare your data set. So you declare your data set by typing to set the year. Okay, so if your data set is monthly, you do say, you write, instead of year, you write month. If it's daily or quarterly, you do that. So you can't do that. You can just use this command, type in there, to declare that your variable time series or your data set is time series. So once we've done that, what we then have to do, we have to just run a normal regression because we're doing OLS. So you just type regress. In this study, let me explain the variables for you so that you will know what exactly we are talking about. We have carbon dioxide, we have carbon emission per capita, So you see CO2 PC. That variable is what? Carbon emissions per capita. Then we have this variable AGPOP. That variable is what? Aging population. After that, I'll give you the topic of this research so that you know what I mean there. Then we have PODEN. That is population density. I'm just giving you the definition of the variables that you see there. So the PODEN is what? Population density. Then we have the URPON. That is urban population. The next one you see is UNEMP. That is unemployment rate. Then the LIEXP. That is life expectancy. Just giving you definitions of the variables. Then the last one is PCGDP. That is GDP per capita. So what you have to understand, and this work has to do with a study titled Impact of Population-Related Variables on Carbon Emission. So we're going to look at how population-related factors.
I think So fast.
Yeah.
Hello?
I'm listening. Yeah, I'm listening.
Yeah, I see in my own variables, I have IN before the other CO2P before PODEN, IN URPOP.
I sent out 2 data sets. We're using the second data set. We are using the second one. The second data set. So check out there. Okay, so once you know the definition of
the second data set is the one that starts with a 1991.
It's the one that
1990.
Yeah, so no, start 1992, 2019. That's the second data.
It's not better you listen to the procedures than maybe you use your own data set to go after it, to go through it later.
Okay, so let's move on. Later, I'll welcome your questions. Don't worry, I'll make time for question and answer, so no problem. Let's move on. Like I said, this data set has to be studied on. We're looking at population factors and how they affect carbon emission, how they influence carbon emission. So here, with this data set, one independent variable here is carbon emission per capita. Then the rest are our regressors. So we'll write, if you want to find the regression, we'll just start regress. We'll regress the carbon emission on this. So we'll type CO2, no, wait, let me come here. Okay, we are using, this data set is the untransformed data. This is a raw data set. Okay, so this is the raw data set. We are not going to use it to do the regression. What we're going to do is that we're going to use this data set now to look at our variable. We're going to describe our variable. Okay, so let's look at the trend. Let's look at the trend of the data set. So first, let's type line. Okay, you type line. We'll then look at the trend, then CO2PC. CO2PC, okay, then year, CO2PC, year, then you write name, okay, you write name into brackets, graph 1, just name it graph 1, okay, graph 1, then just type enter. So we're looking at the trend. This with the raw data set. We also want to look at how the carbon emission trend over time. So if you look at this data set, if you look at this trend, you notice that carbon emission in China between 1992 and 2019 has been upward trending. It's trending upwards. It means that it shows an increasing trend over years. So it means that it has been rising over years now. Now let's do for others. Okay, let's do for others. So let's move on to the next one and look at the aging population in China. So let's look at the trend in China. We are using a raw data set. This one has to do the raw data set. So we'll type AGOP, yeah. Named. So we're going to name this also as graph. We're going to name this as graph 2. We're naming it as graph 2. And we'll type enter. So you can also see that carbon aging population in China has also been trending upwards. Let's look at population density, the trend between that period. So the same line. Do this here. Sorry. You give it a name. So this would be graph 3. So this is our third graph. Yeah, this is our third graph. Just enter, then it will produce. So you can see that clearly it also shows an upward trend. So let's move on. I'll do for some few others, then later I'll just image them, then look at it as one graph. So let's look at the other one, that is urban population. Urban population also in China over that time period. We look at that one too. So we name that one as graph 4. So I repeat the same command, graph 4. this is very easy for you to follow, I guess. So we have that. So this one is very obvious. It's also showing upward trend. So let's look at this. I think we're left with unemployment to so unemployment. Yeah, I'm doing for all of them. Later I'll merge them, I'll combine them as one graph. Name, then graph. This is graph 5. Graph 5, sorry. Graph 5, 1. That, oh sorry, the command for graph 5. So urban population. Now the STATA is very sensitive to variable type in the name. So I made a mistake with a line.
We're looking at unemployment.
Which one? Okay, unemployment. Yeah, unemployment. We did unemployment. It was unemployment, yeah. Unemployment. Yeah. Then we named that one as graph 5. Yeah, that's what I had there. Okay. Okay, so you can see that with unemployment too, it's also showing an upward trend somehow, an upward trend. Let's move on to life expectancy. Life expectancy. Yeah. Name that as our graph 6. I want to be quick with this so that we can do a lot of stuff. Okay. So you can see clearly most of the variables are all showing, almost all of them, they are showing upward trend in case of China. And let's look at the capital GDP, GDP per capita over that time period. Okay, we name that's our 7th graph. So graph 7, name that as 7. So we're done. So when you have this, you notice that it also shows an upward trend, but initially it was not. It wasn't upward, just a little constant. Then it rises, but in all between that time period, it has been trending upward. Okay, let's try to combine this graph as one, because when you are doing a study, you cannot just be saying graph 1, graph 2, graph 3. So the best thing you do is that after generating these graphs, you have to merge them as one, and you paste it in your work. Make it easier for anybody who is reviewing your work to actually follow them. Maybe coming out with a lot of graphs. So let's try this. The command for combining the graphs. So I want us to combine what I want us to do now is that I want us to combine the graphs. You get it? Yeah, I want us to combine the graphs. So this is what we're going to do. The command is what? Graph. Okay. Graph combined. Graph combined. Graph 1. So type graph 1. The space between them. Then graph 2. Then graph 3 in that order. So up to graph 7 and be done. Graph 4, graph 5. So once you just leave spacing to space them, graph 6, space and space, graph 7, enter. Oh. So we're waiting for our combined graph. So that's our combined graph that will be saving. We'll be using.
So this, a quick one.
Can you
can
you drag the graph to the right side so that we can see the command?
Oh, the command are here. You can type them, or you can just take a shot of a picture of it.
No, so that we can type.
Oh, you want to type it? Okay. Okay. If you do, let me know.
Doctor, for example,
please proceed. Please proceed.
Okay.
I'll send the commands over.
Okay, so now let's move on. So if you look at this graph, you notice that all our variables are showing upward trend. Are showing what? Upward trend. This one is just a general explanation you might give. But if you want to explain this, you can also take them like you can say, oh, it increases from maybe 1992 to maybe 2001, then it moves upwards, then it falls, then you see later it rises, then it drops. But what you can do is that you can just look at that between that same time period and look at how the line is trending and conclude that it's showing an upward trend. So if you look at carbon emission per capita, it's trending upward. Almost all of them are all trending upwards. If you look at even with unemployment, you see that initially it rises for some time, maintains some constancy from here. Over here, it's a little constant. Then it rises, it falls, then it rises. But generally, it shows an upward trend. So that would be your explanation. But in your work, you can choose not to spend a lot of time on this if you are doing a thesis or writing a research paper. You can choose to explain them individually or just give a general statement looking at the trend and conclude just write a statement that the variables, mention them by names.
Doctor, how could I explain the fact that the carbon emission is increasing and the life expectancy is also increasing? What would you have to say about that?
What's the question?
For example, if I was doing the interpretation, how could I write the fact that carbon emission is increasing and at the same time the life expectancy is also increasing? Does it like make perfect sense?
The life expectancy is increasing. The life expectancy is increasing and carbon is also increasing.
Yeah.
But if you look at the GDP, it's also rising. So what you have to understand is that when people are earning more, they're able to take care of themselves well.
Good.
You understand? Yeah. Well, I think when we do the regression, because this one will not give you the proper relationship between the dependent variable, because here you with this graph you will not be able to establish the relationship between carbon dioxide, with carbon emission and also life expectancy. For now, it's only the trend that is showing. So it might be that it's showing upwards, but even though because here what you have to understand is that we are looking at how life expectancy is affecting carbon emission. When people are living longer, how is it going to affect carbon emission? So it means that once this life expectancy is increasing, it means that it will also result to an increase in carbon emission. When people are living longer, living well, they spend. You understand it? So with this trend, we will not be able to just establish the exact relationship that exists between those. But unless we do the regression, they will be able to statistically confirm that even the relationship between them are positive or negative, or even there's no significant impact. So when I do the regression, you'll get to understand that. You get it?
All right.
Okay. So, at this point, if anybody has any question, I'll take that before I proceed. Is there any other question? Is there anyone who doesn't understand up to this point?
Hello.
Yes.
Thank you. I understand. However, my history tab is not showing.
Your tab is not showing, really?
The history tab is not displayed on my STATA.
Go to your window. Go to the window and click on history. It will show.
Okay,
go to the window and click history.
Same thing for me. It's not displaying. So that
go to the window. Go to the window. The window from the text bar and click.
Click on the window. Click on history. It will show.
Click on the window and click on history. It will display.
Okay. Okay. So now let's move on now. Any other?
Yes, please. Yes.
No,
yes, I have
please,
a comment.
please. Well.
Yes, I have a comment. I have a comment.
You can give your question.
Okay. Yeah. So please, I just want to comment on maybe the interpretation of the data set. I think maybe it's not necessary, since maybe we have different data set. My data and your data is different. We should focus on how to plot, how to do the work, not the interpretation.
Oh yeah, but the interpretation might not be. It's always the same because when you
the interpretation is okay. The interpretation is okay.
What you need to understand is that if you when you estimated your line and the line is descending downwards, it means there's a negative relationship. It means that over years the population has been falling. But this is showing an upward trend, and that explanation is not different given your data. If your data is showing this trend, then that's the explanation you might give. You understand? But what I'm trying to also say is that you in your explanation, you can even choose to explain from here. You can just look at the trend from maybe 2019.
Excuse me.
Okay.
Could you please go to command bar so we can copy all this so we can understand you more? Remove graph one, go to command, and keep illustrating to everyone.
Okay, so Prof, what he's trying to say is that when you type and then the result comes, you can drag it to the right extreme end so that we can see the command you have already.
Okay. I got you. Thank you. So at this point, I think you can just take short of the command we have here currently. I'll move on, then I'll make sure the next ones I will do that. So if there's not any question related to the trend.
I have a question.
Okay.
I'm not even got to the trend. I don't know if I will have to do this another time. But when I try to paste on the, I go to data and then I go to data editor, and I try to paste my the Excel data. I see that the one I pasted before is already there.
Oh, you just type clear. Type clear.
Go to command and type clear.
Okay.
Then clear it and later paste it. Yeah.
Okay.
Doctor, quick one.
My brother.
Doctor, quick one.
Okay. I want to proceed.
Before you proceed, please repeat the command. We didn't understand.
Oh, the command, I said that initially you have to declare your data set as to whether your data set is times. So you type, once you paste your data into STATA, once you import your data, the next step is that you have to declare your data set to be time series. So you type TSSET, then year. So if it is monthly, you do that.
That doesn't work for me.
Oh, you type this. After you paste your data, okay, after you paste it, just type this. Type T-set, then year. Then enter. Once you do that, it will declare your data as time series.
1 unit. It gave me 1 unit. I don't know what is this. The problem is the name of the data. The name on the data that I have.
Oh, the data set is the second. We are using the second data set I gave you, data set 2, and we are using the raw data.
2.
We are using the raw data. When you want to do the trend, you don't use the transform data. You use the raw data set. So
this raw data I don't have.
Oh, that's been shared with you.
Hello, doctor.
Yeah, please share it in the group now.
Hello, everyone. A minute, please. If you attend the meeting late, you can't be dragging us back. There is a reason why we said meeting starts at 4. I have shared the data into this chat box more than 4 times. Another colleague has also shared it. We've shared it in the group. So when you come late, don't drag us back. 2.
Excuse me.
Excuse me, please.
I actually have a data set named data 2, but it seems different.
We have just 2 hours. Sometimes you will miss something. You wouldn't get everything here.
Okay. Continue. Forget about me.
Please, can I please say something, please? Hello. Hello. Can you hear me? This data you have shared it twice, and I can see the data 1 and data 2. I went back to the data 2 and copied it and pasted, following the same usual guideline that you're giving to us. And the same thing I have on my variable, I have IN before CO2 PC. I have IN before each on the variable on the names.
Exactly.
I still have IN before all of
Please,
the
you can just edit, delete them. I had the same problem, so I deleted those
delete
letters, and now it's responding.
Are you listening? Are you listening? When you open the data set, the second data set, the raw data set, the first column, delete it. Where you see China, delete that part. Because the data sets I got, that's my panel data study, I just copied that out of China for you.
I can't find China on mine. I can't find China on mine.
Can I say something?
The first column is here in my
Hello, everyone. Please listen. I think the problem is that. Hello, everyone. Hello. When you open the raw data, in the Excel sheet, there are different sheets, 2 sheets. Just go to the fourth sheet. Go to the fourth sheet. The fourth sheet is showing the raw data. The normal sheet that is opening is the raw data. Just go to the raw data, delete the country there, and use the data. That is just the simple thing.
That's what.
Hello, sir. Please, can I speak?
Thank you so much.
Hello, please, can I speak?
Please.
I feel like the presenter and some people don't understand what's going on. I understand what majority of the people are saying. There is an issue with the headings where we have LN, IN. So for those having those problems, please just delete it.
Are you listening?
Just delete it, because I had the same issue. I deleted it and everything is fine now. Where you see LNC2PC.
Please, can we proceed? We are quiet because we have done the right thing.
Yes, I have
time. Can we please allow the
Please let me come in. Please let me come in.
I've got that now. I think I know the problem.
Time, please. Can we please
let me
allow
come
the
in.
presenter? The time is limited.
Those of you who are seeing LN at the beginning of your variable, it means you are using the transform data. Those of you who are seeing LN at the beginning of your variable, it means that you are using the transform data. The raw data. We are using the raw data at this time. So those of you, if you notice that your variable is LN, then the variable will continue. That is what the transform data set. That's not what we're using. We're using the raw data sets. The raw data set doesn't have the variable name LN. If you have LN begin with the variable name, it means that data has been transformed. That's a transformed data set.
I have got that.
So we'll come back to use the transformed data set. So please notice that and let's make that correction. Now let's move on. The next thing we have to do is this. We have to look at the stat.
Guys, let's move on and we'll proceed.
Why did when I imported everything, it's showing how in.
No, what we done is just
Hello, everyone. Sorry, I apologize. I have to mute every one of you. Dr. Pixon, please give me a minute. I have to mute every one of you. Last week, we had the same issue. Can we allow the presenter to work? When he calls for questions and the question comes, let only the presenter address the question, and then we move on. Please, we are taking this training a little bit wrongly. Let's all exercise decorum. I will allow the presenter to unmute himself and then go ahead with the presentation. We will mute everyone until the presenter asks if people can ask questions. You put up your hand, he calls you, and then we will unmute you. If you have any question, paste them in the chat box. I will respond to them, or when it comes for questioning time, he will respond to them. Thank you so much for understanding, and sorry for muting you people, but I think we have to. So, Dr. Pixon, kindly unmute yourself.
Let's move on. let's move on. So the next thing we have to do is here is that we have to what? We have to explore our data. So that's one of the way we explore our data is look at the trend. The trend analysis, the graph thing we do is part of it. We exploring our data. We want to, now let's proceed to looking at statistical description of our data set. So you type, if you want to look at the statistical description of the data set or our variables, you will type sum, and then you type all the variables that you are using. So sum, then you type the variables there. Let's look at that. What is your understanding? And what if you want to do this part, you always have to be sure that you use your raw data set, not the transform data set. If you want to look at the trend and also the descriptive statistics, always make sure you use the raw data set, not the transform one. Now let's move on. Okay, so what I've done is I just typed sum, then continue with the rest of the variables that we are using. So that's what I've done. You enter. So you would notice that our observation is what? Is 28. That's our observation. Then it tells you, it will give you the mean, the deviation, and the maximum value of the data set, and also the minimum value. So if you look at carbon dioxide, the average is what? 4.7 on average. So it means that on average, that is the per capita carbon emission. Then you look at how it deviates from the mean, so that standard deviation. So you just record this one, then you record them. So here, once you have this data set, okay, once you can use this, you can just design this table. You can let it look like this, or you yourself can choose to design a different way and report it in your study. So sometimes some people will just bring the variables at the top, then also bring this description, this writings to the other side of it, and make it your observation, means that. So it depends on how you want to design it. But on the day, you can also present it just like this. Then what you do is that you just will try to describe your variables. So yeah, you say that, oh, on average, between 1992 and 2019, the carbon emission on average 4.74, and the deviation was 2.1. See, then you also will talk about the maximum and the minimum values. So here, just that you just report this thing descriptively. It's very easy. That's what you have to do. Just when you go to aging population, you can say that on average, the aging population on average is 7.79. Then the deviance is 1.5. Then you talk about the minimum. And that. What you have to understand is that these are the aging population you have here. It's measured in percentage. So the main reason we are using the raw data is that when you are discussing this statistics we have here, you have to use their unit of measurement. That's what you use their unit of. That's the main reason why we are not even using the transformed data set. We're just using the raw data set. So in discussing that, you have to make sure that you talk about their unit of measurement. So when you say 7.79 aging population, then this one is in percentage. It's in percentage. So it means that on average, between this time period, aging population average 7.8. 7.8. In that year, and the deviation from the mean is 1.52%, because the unit of measurement is in percentage. If you look at the population density, it has to do with kilometers per arable land. So kilometers per arable land. So you look at the land that the population are covering. So here, the sample size is kilometers per what? Arable per land. So that's the measurement. So you discuss them by also recognizing their unit of measurement. So when you are talking about, make sure that you add their unit of measurement also to that. Okay, so this is what I want to teach you with this one, with the raw data set. With the raw data set, these are the tests that you have to do. So in your studies, whenever you want to look at a trend or the distributed statistics, always try to use the raw data set. Any question? Any question from here? If there's no question, then what we'll do is I will end this. Then we then go and take the transform data. So we are now going to use the transform data to actually, okay, I think I noticed.
Yeah, doctor, there are two hands up. And I think the feedback I'm getting is if you could slow down a little bit in the presentation.
Okay.
Thank you so much. But there are two hands up. So the first one.
Okay, Don and Sam. Because Sam. Okay, Sam and.
You can unmute yourself. Don, unmute yourself.
Sam's.
Hello.
Okay, Sam. Yes.
Yeah.
Sam.
Unmute. Okay.
Why you
Doc? Yeah.
No, one after the other. Don.
Don't pitch.
Okay. Why you are clearing our variable to time series? You use yearly. What if I want to learn my analysis quarterly, monthly, weekly, and daily as such maybe? How do I go about it? You just replace the year with months or?
No, I told you, actually at the beginning of the presentation, I told you I said that the times it can be in different form. It can be a monthly data. It can also be quarterly or yearly. So it depends on the data set that you are using, you are using. So if you want to, in your study, if you want to use monthly, then you look out for monthly data sets and use it. Actually, STATA doesn't have the function with which you can use to transform your data to monthly and quarterly. If you're familiar with this one, if you have a function with which you can use to transform your data into quarterly and other form. But STATA doesn't. Either where you are getting your data, the data is also being provided already in monthly or quarterly or whichever form.
Yeah.
You get it? Normally, when you go to the World Bank, most of their data are yearly. So when you get that yearly data, you can, if you know how to use data at this, if you have a function that can help you to then convert your data set, which are yearly, to monthly and quarterly.
Okay, let's imply I have monthly data sets. So I substitute year by month.
If your data set
line and variable then year, so I substitute year with whatever.
By month. So it may be if let's say if you have your data set are in monthly, so you write maybe 1991 month 1 January, and so it will be month 1, month 2, month 3, month 12. You understand? Knowing that the month 1 is January, that's how you present your data set.
Okay.
Yeah.
Thanks.
So sometimes it depends on where you're getting your data set. The other sources where the data set are already presented in quarterly, so that one is easy for you to start with that kind of situation. But with this one, is in yearly form. Let me talk to Frans.
Okay, Doc. Please, I got lost somewhere where they mentioned the raw data set, and the one I imported is the process data set that has LNCO2PC. So how can I convert this to raw data set?
Oh, the data set that has been given to you already are in two sessions. We have the raw data set and the transform data set. Then I said that we're going to just use the transform data set data, but the raw data set, we're just using it to look at the trend and also the distributed statistics. That's all. So after this, we're done. We're just going to turn to the transform data. So if you have the data set, when you open, you will see it. You will see the transform and the raw data set. The raw data set, we're just using it for the descriptive and the trend. After that, we are done with it.
Okay, because on the Excel sheet, I had data 1 and data 2. And
the one we are using the data 2.
We are using the data 2.
Yes.
Okay. On the data 2,
yes.
I couldn't see the difference between the are there two?
The data 2 we have when you open it,
okay.
we have the.
I've seen it.
Yeah,
I've
make sure
it.
that with the data 2, the raw data, the first column, delete it. Delete the first column where you see China.
Yeah.
Yeah.
Okay. Okay. I think that is where I got a bit confused. Thank you so much.
Okay. Let's now proceed. I think we'll be doing a lot of stuff later, so let's now proceed now. Let's look at this. Let's now type clear. So please, you type clear because we are going to use a different data. So type clear. Let's clear this data. So you clear it. Okay. We're done with this data set. And we're done with this data. So let's now turn to the transform data set. Transform data set. At this thing. Okay, so I now goes to copy the transform data set. So I'm copying the transform data set. Okay, so I come to, let me save this. Okay, so let me now, I'm importing this, so I've just copy and paste it. I just copy and paste it. Just the same procedure we use. We're now making use of the transform data, so please do the same. If you are following, just do the same thing. Okay, we're done. So you minimize the, get to the command. So what you have to understand is that we've imported new data now. So the next thing we have to do is that we have to declare that our data set is to time series. So you type that. We declare our data time series. Are you done? Okay. So once we've declared our data set to be time series, we then have to go ahead and do a regression. So we now regress the carbon emissions on aging population, population density, urban population, and stuff. That's what we are going to do. We are going to regress that on that. So we type regress, REG. Then we begin with the independent variable. So here, when you want to find you want to estimate OLS, after you type the regress, the next thing is that you type your dependent variable or the regressant, what we call regressant, or the explained variable. That's what we begin with. So you type that one. So ln CO to PC, like that. Okay, let me first, before we do it, let me first tell you something. The data here has been transformed. I don't know whether last week when we were teaching data management and stuff, we were taught how to transform a data set. But what I've done is that with the raw data sets, I just find a natural log of it, natural log of this data set. So I can, I don't know, Kwame, if you can hear me, Kwame, can you answer this? Hello, Kwame.
Yeah, hello, doctor. Just last week we didn't do data transformation, so if
okay,
you have
so
time,
okay, then I think okay. So let me look at that. Let me launch my this thing, something before I get back. I don't want them to. How can we are using transform data? What you have to understand is that the raw data sets are in different units of measurement. All of them, they all find themselves in different units of measurement. So to make it easy for you to interpret your results, we then have to transform all of them into natural logs. Once you do that, it makes it very easy for you to do your interpretation. So if you transform the data into natural log, then it means that you can then explain the variables in the form of percentages. You understand? So, 1% change in this will lead to that. And because the variables are in different units. So once they are in different units, we just want them to come have a common unit of measurement. So here we're just transforming all of them to natural log. But one thing you should also understand that sometimes when you are doing the natural log and any of the variables have a value which is negative, you will notice that you will not be able to convert that variables series into natural log. When it happens like that, just leave it. When it happens, let's say your variable that you are transforming, it has a negative figure. You will see that when you get to that part where it is negative, it will be like a missing figure or something. It will not be able to convert it to natural log. So when any of your variable has value that is negative, then that particular variable, just leave it in that form. So when you are doing your explanation, when you get to that point, that session and that variable, you don't explain them in the form of percent unless its measurement is already in percentage. If not, you just have to say, well, a unit change in this will lead to this number of quantity. Then you use that variable's unit of measurement in your explanation. That's what I want to tell you here. So let me first show you how you can do this natural log transformation. Let's look at the carbon emission. So let me name the variable ln, then carbon emission. Because I'm transforming them, I want to show you. So PC. Okay, you just begin with ln, then PC, CO2 PC. Then let's come to the second row under the variable that we want to transform. So look at this. You type equal to, then ln. That's a natural log. ln. Then you open a bracket. Then you go and highlight the variable you want to transform. So you go and click on the carbon emission for 1992. Then you close your brackets, then enter. So you see that variable now has been transformed. Let's do it for the second time, then we can drag it. So you type equal to, then ln, then open a bracket, go to 1993 under carbon emission. You highlight that one, then you close your bracket. Okay. So what the next thing you should do is just highlight these two variables, drag them, then you click on the right corner, the down part of it. It will give you just after you highlight it, you see that when you send your cursor, it will be showing a plus sign. Okay, so you click on that to look for it will give you the other series. Okay, so you see that. So this data has now been transformed. We have found the natural log of carbon emission per capita for that given period. So that's what I did for all the variables. So I repeated the same thing, then later I copied them here. So I think I just perform one example for you to understand. So please try and follow it. Just use the subjects equal to ln, open a bracket, then go to the variable that you want to transform. So in this case, aging population. Highlight, you click on it, then you close the bracket, enter. Then you come to the 1993 value for aging population. You type equal to, then open a bracket, then click on the variable, the series for the value for 1993 under aging population. Close the brackets, then enter. So after that, you highlight the two variables, you drag it down. Just click on the down part, the right corner there, you see a plus, you just click on it. And that one also will transform the variable. So I'm going to pause here, then get back to our estimation. Okay. So this is it. This is how the data were transformed. Now let's move on quickly. Let's move on quickly. Now that you understand how the data was transformed, let's move on quickly. Now let's come here. So like I said, you type regress, then you begin with the dependent variable. Dependent variable in this case here is what? Carbon emission, because we are looking at how population factors will influence carbon emission. So our dependent variable is that. Look at that. So just type the variable, then you just space them. Just write the variables down and space, make sure that there are space in between the variables. Okay, the last one is per capita GDP. Okay, so we're done. So once you do this, the next thing, once you're able to, you finish writing it, the next thing you do is enter, and your result will be given to you. Okay, so it's here that the guy was asking the question, how do you call, how will life expectancy influence carbon emission? You'll be able to know whether life expectancy actually has any significant impact on carbon emission. So let's look at this one. First, what you need to look at here is that I will come back to explain the variable, but you have to make sure that the model is actually fit to explain the carbon emission. So what we have to understand, we have to make sure that the independent variables are fit in explaining the carbon emission over the years. So we do this by looking at the result for F statistics. So the F statistics here, the F statistics have to be significant. So when the F statistics is significant, it means that our model is fixed in explaining the carbon emission. So you have to always measure, once you do the estimation, you make sure that the F statistics is always true. It has to be significant. If it's not significant, it means that the regressors are not fit in significantly fit in explaining our the dependent variable, which is carbon emission. That's what you have to do. Then let's look at the R square. The R square here, it tells us how the percentage change, how the change in carbon emission are explained by changes in the independent variable. So it means if you look at the R square we have here, we have 99, and you have 0.9966. That's what we have for the R square. So it means that the 99.7% of the changes in carbon emission, it means that 99.7% of changes in carbon emission are explained by the changes in our regressors. Our regressors we are talking about here are our independent variable. We have the aging population, the population density, urban population, unemployment, life expectancy, and also our income level. These variables explain 99.7% of changes that we have in carbon emission. So now let's look at how those individual variables, actually the impact of the individual variables on our dependent variable, which is carbon emission. So if you look at the coefficient for aging population, it's negative, but it's not significant. If you look at the p-value, it is not significant. So it means that the aging population has no impact on carbon emission. That's what it means. Because if the p-value tells us that it's not significant, it means that the coefficient value that we are seeing here, it is not different from 0. It means that the coefficient value that we are seeing, it is not that different from 0. So it suggests that aging population has no impact or has negligible impact on carbon emission. In this regard, in China, that's what it means. Let's move on to population density. Population density also record a negative coefficient, which is 14.36, and it is significant. So it means that there's a negative relationship between carbon emission carbon emission and population density. So it means that a 1% change, 1% change in population density will lead to 14.36% change in carbon emission. That's what it means. If you look at urban population has a positive coefficient. It is also found to be statistically significant at 1%. What you have to understand that in doing this, you always have to look at your confidence interval. So the confidence interval here is 5%. Here is 5%. So it means, but if you consider even the p-value here is less than 1%. So it means that our the urban population has a highly significant impact on carbon emission. And that there's the relation between these two variables is direct, is positive. There's a positive relationship. So an increase in urban population will lead to 9.73% in carbon emission. That's how we explain it. We always will look at the sign of the coefficient and relate that to compare that to the p-values and see whether it is significant or not. So if you look at the unemployment, even though the unemployment has a negative relationship with urban population, carbon emission, it was not statistically significant. You can see that it is not statistically significant. At even 5% is not. So it means that unemployment has no impact, because once it is not significant, it means that the coefficient value here that is not different from 0. So here we can conclude that unemployment has no significant impact on carbon emission given the time period. Then let's look at life expectancy. Life expectancy is negative 29.89%, and it was also found to be significant. So life expectancy has a negative impact on carbon emission. So for our result, but later we'll look at whether we'll look at other problems to know whether the results are not misleading. So don't worry, but I'm just trying to guide you as to how you can explain this. Let's look at the last variable, which is our per capita income. So our income level has a negative relationship between carbon, but that was not statistically significant. It was not statistically significant. What you have to understand is that as people's income increases, as our income increases, we want to live in a clean environment. As our income increases, we want to live in a clean environment. So it means that our income should have a negative impact on the way we emit and how we degrade our environment. But given our result here, even though the relationship between income and per capita here is negative, it was not found to be statistically significant. So it means that per capita income here has no significant or has a negligible impact on carbon emission. You get that? Okay. So at this point, I will welcome your questions, or if not, we can just also proceed to look at
Doc, please, I think there are someone wants to ask a question. So okay, let's take one. Okay, so Sam, okay, please unmute yourself and then ask your question.
Okay.
Yeah,
okay, I'm listening.
Hello, Doc. Using the same data set, I did something and the result I had on my own is different from the one you have on your system. So I don't know what could be the reason.
Which one? Check your variables. Did you estimate for the variables we have?
Yeah.
And are you using the transform data?
Yeah, I'm using the transform data.
So what was your what was the independent variable you used? What was the independent variable? The dependent variable. What's your dependent variable?
LNCO2PC here.
Yeah, that's your dependent variable. Yeah.
Yeah, and under it you have LNAGPOP, LNURPOP, LNUEMP, LNLIEXP, LNPCGDP. So if you come to coefficient, under coefficient, you have minus 2.5, and I have minus 1. I have minus 1.47187.
So it means it might depend on the version of STATA you are using. Which version are you using?
Okay, that is STATA MP15.
Okay, I'm using STATA 16. So it depends on your version.
Okay,
so you can see that depending on the version you are using. I'm using 16 now.
Because when you look at the LNURPOP, yours is having minus 14, and where here I'm having positive 3.10119.
Which one? Come again.
Doctor.
On the second one,
yes,
I'm having positive 3.10119.
Population density, yes.
Yeah, population density, and you're having negative.
Yeah.
Okay, so doctor, how about Sam? You send your screenshot to the group, because if you don't have all the variables here, you definitely have different coefficients.
Okay, let me
so
let me send this.
Send it. Let's review. Okay, and then maybe we should ask destination to mute himself and then talk.
Hello, can you hear me?
Yes, please.
Yeah, I can hear you.
Okay.
Can I talk? Who is speaking?
Destination. Okay.
Okay, so first I said thank you for your presentation. I just have a few questions. So I just want to know the inferential significance for the confidence interval, the t statistics, and the R square. So how is this significant when you're trying to make inference?
Oh, you see, when you're doing a study, actually when they are teaching you econometrics, they will talk about the t statistics. The t statistics actually will help you to explain the significance of the individual variables, like each. It helps you to talk about the significance of each variable you have in the model. But the F statistics will actually talk about the whole model, how those variables are significant in explaining the dependent variable. So when they're teaching you econometrics, you know that when they are focusing on T ratio or whatever, all what they are trying to tell you is they are trying to let you understand the significance of a particular variable in the model. That's what it does. But if you look at the F statistics look at the significance of the whole model. That's why I'm saying that if you get the F statistics not to be positive and not to be significant, then it means that your model is not fit to us. Cannot jointly significantly explain the dependent variable. So for the T, it just give an explanation for the individual variable you have, all the separate independent variables. I hope I answered your question. Are you answered? Hello? Okay, let's move on. The next person.
Hello.
Yeah, I was asking whether you were answered.
Yes, I got that. What about the confidence interval? How is this statistically significant?
Which one?
The confidence
interval. Is it the R square?
The 5% confidence interval.
But the confidence interval is just like, look at this. If you look at the confidence interval, what was it? 95% confidence interval. So it means that your study, or your model, the result that you're coming out with, you are 95% confident of your outcome. It means that your error margin is what? 5%. Your error margin here is 5%. That's what it means. So it means that on the whole, your confidence level of your work you are doing is 95%. And your error is what? It's 5%.
So can you give an example using
okay, let me okay, so let's look at something. Look at this. If you take the let's look at this aging population coefficient. You see the aging population coefficient, okay? For this aging population coefficient to be significant, for this aging population here to be significant, then it has to fall. It has to fall in between the confidence interval, because this is your confidence level, with the level at which that variable is significant. So if you take this coefficient, you'll notice that the aging population coefficient, it doesn't fall in between the interval. This is the lower interval and the upper interval. But look at the coefficient, it is negative 2.517, which will be outside the negative. So it's outside of it. So once it's outside, it means that it's fall within the error. So you can just even use the confidence interval alone to determine whether your variables, your independent variables are significant.
Yeah,
once
thank
they
you.
fall in between the confidence interval, then they are significant. Yeah, any question?
Thank you.
Okay, so the next one is BNTY. Kindly unmute yourself and then.
Okay, thank you very much for your lecture. I so much appreciate this. This particular type of teachings and the data is what is directly related to a kind of something that I am doing. I actually have a raw data that involves experiment that is conducted on two separate buildings that involve parameters on temperatures, relative humidities, and air qualities, and even CO2. But when you look at this, some of these variables involved in this are variables that have unit. For instance, temperature, relative humidity. So in this case, and although I have one or two parameters in this that doesn't have a unit, in this case, can you go ahead to transform this kind of data that is being recorded?
It means that your data, it suggests that your data is a survey data, is that not so?
Yes.
Yeah, if it's a survey data, you can still use the regression, but you are not, it's not, you can still use the regression. It means that your data isn't a time series. Because it's a sessional data, meaning a data for a particular period, a particular instance. So you can still do estimation.
Okay. And another question, yes. And another question again is that this data, for instance, the experiment from the buildings are something that is time bound, recorded with times in seconds or something within 24 hours. Within 24.
So that data, if you are recording the data set, you can choose if their values are too huge. What to do is that you normalize them. Let's normalize them by finding a natural log of all those variables. If let's say that data set you have income in it, you find a natural log of all the income, then use it. So you so you can find natural log. But the thing is that, like I said, if some of the values are negative, you cannot find a natural log of a negative variable. So when it happens like that, then that particular variable just have to leave it. If any of the series is negative, you just leave it.
Okay. And the other question again is in terms of maybe correlation or comparing these two separate experiments, because these are experiments that are running concurrently. For instance, you say building A, building B. You place an equipment on building A and place an equipment on building B at the same time, trying to record this value of the or parameters you are looking for. Are you going to, when you are trying to copy these data and impute them on STATA, is there any possibility, because the data are enormous, they are much, is there any possibility that you copy both of them and place them side by side on a page of the STATA that you are running?
You can prepare your data in Excel. You can prepare your data in Excel, then import it, or just copy like the way I did and paste it there.
Okay, and the last question is that, Doctor, I noticed that maybe along the line, I noticed that you are in Chindu. Maybe once in a while, I will try and meet up with you to explain some things in detail.
No problem. Later, you can take my WeChat from Kwame.
I think I have seen your WeChat on the Black community in Sichuan. So possibly I may.
I've been fighting there. You know me. That's I know.
All right, I'll take your WeChat from Kwame. Yes, thank you. Thank you.
Okay, so doctor,
okay, my
I think one person has a question, but I'm unable to find the person. So
okay, then let me go on. Later I'll come back. Then we can talk.
Kindly let him ask. Kindly let him ask. I don't know why he's. Oh,
okay.
Sorry, I cannot find you because a lot of people are using UID or AAD for their names. You've only lifted your
so
hand.
You will not be able to tell their names.
So I cannot be able to identify. So we move on. Sorry for that.
Okay, now let's move on. So now, after we've done this, the next thing that we have to do is that we have to ensure that our model actually meets the assumptions of OLS. So like I said during the presentation, I didn't give you, I didn't go through it, but I'm sure you know the assumptions, the axioms of OLS. One of it is that it has to be linear, and also what normality of the errors. So we have to look at all those assumptions. We have to test them and make sure that our model actually meets, it doesn't suffer from any of those econometrics problem. So we have to do the diagnosis test quickly. If any of the problem, or if we are not able to meet any of the assumptions, then it means that we have to use a different method. It means that our result might be misleading, so it's appropriate we use another method. So let's look at the test. I have actually about 3 models I want to run. I want to practice them too, so I want to be quick. Let's do this. So if you want to test for normality tests, if you want to look up for the normality test, you type S. You can see when you want to test for normality, you can use Shapiro or you can use histograph. So there are a lot of tests you can use, but in this case, we are going to use Shapiro and Wake test for normality test, the normality of the residual. So we type SWLK, you get that one. Okay, but before we do that, let's predict the error. Sorry, we just have to do predict errors from our model. So let's predict an error. So predict residuals, and we type. So once we have predicted an error, then we type SWILK, and then type our residuals. So we have already predicted. So we want to test this residuals to know whether our errors are normally distributed. Okay, so this is the test. If you look at it, you can see that it is significant. So it means that the errors from our data is not normally distributed. So it means that our model suffers from normal distribution. It means the residuals are not normally distributed. So that's one issue we have here. Let's move on to, let's look at multicollinearity. Okay, multicollinearity. Let's look at something. These are the independent variables. So if you look at the independent variables, they don't need to correlate among themselves. So if the errors from this, if these variables, the dependent variables are correlating among themselves, it means that it is very difficult for you to know the specific impact of a particular variable in the model. So let's say population, aging population it has a positive correlation with life expectancy. Then, or let's say urbanization has positive correlation with income. Then it means that it's very difficult for you to tell the exact impact of urban population on carbon emission, or it will also be very difficult for you to know the impact of income also on carbon emissions. So this is what we have to ensure. We have to make sure that that linearity is very minimal. The association between these independent variables are very, very minimal. So we have so many ways we can also test for this. Okay. We can first, you don't need to look at how they correlate with the dependent variable, because we expect that per the assumption with which we selected our variables, we assume that those variables have some level of association with our dependent variable. So what we'll do is that we are going to do what we call contingency test. Contingency test. It's just like a normal correlation test, but in this case, you don't include the dependent variable. You call it contingency test. So you type CORR, then the variables. For me to be quick, let me use another way that we can be quick with it. Okay, so just type CORR. You exclude the dependent variable in this case. We exclude the dependent variables because the assumption which we selected our variables, we know they will surely have some association with the dependent variable. So we want to see the specific impact of our dependent variables, regardless of other dependent variables. So let's look at this. We look at this test, as I said, we term it as what? Contingency test. It's a correlation matrix. This is a correlation matrix that excludes the dependent variable. So this is a contingency test. This contingency test here, if you look at it, you can see that there's a high association between aging population and population density. There's also a higher association between urban population and aging population. If you look at if you look at the aging populations, it has a very high association with the rest of the variables. So when it happens like that, it means that you have to, that variable that is highly correlated with the other, you have to what? Exclude it from the model. Whenever you notice that there's a high association between two variables, you have to what? Exclude one of them. You have to what? Exclude one of them. Sometimes you want to include them because of if you want to include them, I will later will show you how you can include them in the reasons for you. But the best is that when there's a high association, you have to what? Exclude that variable that has high association with other dependent variables. And if you look at population density with urban population, it also have the same thing. Actually, all our variables has a very high population, a high association with each other. You can see, so there's a problem of multicollinearity with our variable. You can see that. It means there's a high association amongst our independent variables. That's what it means. So when it happens like that, then it means that you have to, then it means that your results that you use generate from OLS is what? Very, very misleading. So it is therefore advisable that you use other variables, other tools, other methods that are more robust or that account for multicollinearity to use. It means that it is not appropriate for you to use OLS. When you have to notice that there's a high association among the independent variables. So let's look at something. If you see the correlation result and they are around, let's say 0.4, 0.5, this is a very moderate association. So that one, you leave it, okay? But when they are 0.8, 0.9, this is very high because they are actually going, if you approximate them, they will be equal to 1. It means that there's a perfect association between those variables. So when you can see that they are very high, 0.8, 0.9, this is a very high association among the independent variables. So it means that our model also suffers from multicollinearity. Now let's move on to the next one. Let's test for this. Let's test for this one. Okay, we can also use this. Let's look at this. We can also use variance inflation factor in doing that. So you can just type that. Okay, so with this, so you can see that there's what you have to understand with the vector of variance, your score, your score there, your vector of variance score should not be more than 10. Should not be what? More than 10. So when the score, the VIF, the score is more than 10, it means that there's a problem with what? There's a problem of multicollinearity when the score is greater than what? 10, then it's highly correlated. So if you notice, even on average, the mean variance inflation factor score is 893.34, which is also higher than what? 10. But when you read the literature, some of them will tell you that the score shouldn't be more than 5. Some will tell you that some will tell you, oh, the score on average should not be more than what? Should not be more than 10. So it depends on the literature you are using to argue. It depends on the literature you are using, but you can say the score, if the score is not more than 5, then there's no multicollinearity. But once the score is greater than 10, then there's a problem of multicollinearity. This score here is greater than 10, so there's a problem of multicollinearity with our model. If you look at this one is the tolerance. This one, it shows the degree of tolerance of that collinearity amongst the regressors. This one is we have 1 divided by the vector inflation factor. This column, the values you are seeing here actually suggest to us about the degree of the collinearity amongst the regressors. So that's what we mean by our focus is always on this one. Once the score is greater than 10, that means that there's a problem of multicollinearity. That's what you have to know. Now let's move on to the next thing. The next thing here is that we have to test for homogeneity of the variance. Homogeneity of the variance. Homogeneity of the variance here, I'll get back to show you the assumptions so that you know exactly which ones that we're talking about. Let me try to show you so that you guys can follow. Okay, let's look at this. I will get back to show you the result. We're looking at this. Okay, so these are the assumptions. These are the assumptions that we are looking at, okay? First, we have to ensure that our model is linear. The relationship between the dependent variable and the independent variable are linear. Then the errors should be also normally distributed. Then we are looking at the homogeneity of the variance. So it means that when we have to ensure that the coefficients are constant. So we are looking at the homogeneity of the variance. So here, we are going to do that test. Then we also have to look at the independence of the errors. What you have to understand is that when you look at observations, let's say you look at let's consider, let's say, aging population. The aging population, the errors related to that aging population, let's say for this year, should not correlate with the errors of the previous year. So when there's a serial correlation of that, it might also have an effect on it will cause our result to what is aging. So we have to ensure that issue doesn't exist. So we'll look at the serial correlation, or what we call autocorrelation. Then we'll look at whether the model is well specified, or whether we have omitted some relevant variable, or we have included an irrelevant variable, which will make our model to be what? Misspecified. So we'll look at all those ones. So these are the assumptions that we have to make sure that we meet. Once we meet this, then it means that our results are not biased. So let's get back to our STATA whilst we look out for the rest. Okay.
Hello, Doc.
Yes.
A moment. Because I'm going to share your WeChat in the group because almost everyone is asking for your WeChat now. So
okay, let's do that later. Let's do that later.
Okay,
let's move on.
What I'm saying is we have 3 people on board who wants to ask questions. Do you mind taking them before we move on?
Okay, there's no problem.
Okay, so please, the first one is OAD, UIB can you unmute yourself and ask your question?
Yes.
Yeah, I'm listening. Yeah, hello. I'm listening. Hello.
UIB answer. UIB OAAD. Please unmute yourself and ask your question.
Yes, you can hear me.
Yeah, I can hear you.
Yes, the question I wanted to ask is on the first table of regression that we did.
Which one? Is it this one, the correlation, or the regression result?
Yeah, the one on top, the one on top of this one, after, before we do the prediction. Yeah.
Before we.
Here, yes.
This one.
Here, yes.
Okay, that's the. This one is a test for the. We have to ensure that the errors are normally distributed. So that's it. That's what we need to. I can show that graphically,
yeah, so
but what you have to when it.
My question is on how you interpreted the second variable, which is this here. Our population is related to the carbon. Yeah.
Yeah. This okay.
Yes,
you are talking about the contingency test. Okay, the contingency test is for us to look out for the multicollinearity of our regressors, the independent variable. What we have to ensure that our independent variable.
Not contingency test. Not that one. Not that one.
The Shapiro.
I think it was and weight regression.
Which one? Regression. The regression. Oh, okay.
The table just above this prediction.
Okay. I'm showing that.
Yeah, this table here.
What's the question?
Yeah. Okay. So my first question here, when you doing the interpretation of variable this population, against the dependent variable, the carbon, you said that actually we can see that it is a negative related to carbon, and you said that it was a 1% change in population.
Yeah.
How does it react with the carbon dioxide? It is because here we have negative. Does negative mean?
What I'm saying, okay. So what it means is that once you see the sign to be negative, it means that it means that if aging population increases by 1%, carbon emission will reduce by by negative 2.5. That's what it means. But it is not significant because it is not different from zero. If you look at the p-value, it is not significant. Even though a 1% increase in aging population will decrease carbon emission by this margin, it is not statistically significant. So it means that the coefficient here we have is not different from zero. So it means it has no impact on carbon emission. In our conclusion,
okay,
that's what it means.
Now clear. Then the last question, the final one, on the probability of F.
The F statistics.
Yeah, it is statistically significant because we have 0.00.
Yes, yeah.
So my question, if we have, for instance, let's say it is statistically significant, like it is 0.00, but now when we come to the table, you find that maybe all the variables we have here are not statistically significant to the dependent variable. What can you say about the table? Can we still go ahead and say that our table is correct?
So it means that you have to do other tests, then you change the method. In that case, you have to change the method.
Okay.
Because if the F statistics is significant and almost all your variables are insignificant, they have no significant impact on, then you have to change your approach.
All right.
You have to use a different estimation method. Yes. Any question before we move on?
No, that's okay. Thank you.
Okay. Then now let's look at our test. Now let's test for.
Hello, doctor. Please, I think there are some questions
Okay.
Yeah. Yes. Can you hear me?
Please, one question per person. Let's be fast because time is up.
Okay.
Okay.
Looking at the time, I think I have to extend it so that I can teach you guys what I want to teach you.
Okay.
Okay, so don't worry, I'll give you some extension. Let's move on.
All right. So can I ask my
what's your question? Okay, okay, ask your question.
So I think you were moving too fast. There are some basic concepts that I couldn't get. So I just want to know.
Ask that.
Yeah, I just want to know, how do you determine the kind of model or test that is appropriate for your study based on the results from the correlation metrics, based on the results you got from the correlation metrics? How do you determine the right test or the right model for your study?
Yeah, I'll tell you that. After the test, I will tell you that given the results you've gotten, it's not appropriate to use that method, and I'll suggest method you can use.
Okay.
You get it? Okay. Okay, so let's move on. Any other question? If not, we can move on. Okay, so now let's try to test for homogeneity.
Doctor. Sorry,
yes,
we
my
have
friend.
2 more. Hello, doctor. Sorry, we have 2 more.
Okay, okay.
So.
Okay.
Yeah, DC.
All right. Thank you so much. Can you hear me?
Yes, please. Let's go direct to the question.
All right. So I wanted to ask a question on the matrix, the correlation matrix. I understand it, but do we have a specified standard for the correlation that helps to drop or maintain some particular variables? Say maybe if the correlation between 2 variables is 0.5, 0.2, 0.8, which is the standard of, say, yeah, that's the question. Thank you.
Okay, what you have to understand is that when your correlation coefficient, let's say is above 0.7, or let's say 0.7, 0.8, 0.9 upwards, it means there's a high correlation between the variables. When it is around, let's say 6, 5, or 4, it is a moderate. There's a moderate correlation among them. Then when it is 0.2, that means 0.2, 0.1, it means that there's very low association among the variables. So what you have to understand is that we only would drop the variables when we find out that the association between them are high. Okay, so when it is 0.8, 0.9 going, then it means that those variables that correlate with each other, one of it has to be dropped. One of the variables need to be dropped. So this is how you do it. If you want to drop one of them, what you first do is that you put all of them, all the variables, those variables that they correlate with each other, you put them in a regression. You run them. You look at their R squared. You look at the R squared. So what you do is that you put all of those variables that are correlated among themselves, you put them into a regression. Then you run them and look at the R squared. Okay. So when you look at it, when you run it, and the R square, you record it. After that, you drop one of them. After you have put all of them into one regression model and run them, you record the R square. Then later, you will drop one of the variables which are highly correlated among themselves. You drop one, you drop one from the model, then you run the regression, then you record the R square. Then after that, you drop one, then you bring another one that you drop and run a regression and look at their R square. So if the one that when you put them into the model will give a high R square, you maintain that one, then you drop one. You understand? That's what you have to do. So if, let's say, in our case here, we have aging population highly correlated with population density. So what we do is that in our model, we include all these variables that are correlated among themselves. We run it, we record the R square. Then after that, we drop, let's say, aging population. Then we run the regression, we record the R square. Then after that, we drop the population density. Then we include the aging population, and we run the regression. Then later, we record the R square. So what you do is that you then have to decide based on their R square, which of them that when you include them into a regression, it gives you higher R square value. Then you drop one.
Okay,
you get it.
Doctor.
Yeah. So normally you include them in the model. Okay.
Yeah, we have one last question. So please, Barnabas, kindly unmute yourself. Hello, Barnabas.
Yes, sir. Yes.
Yes, please. Yeah. So
can you hear me, doctor?
Yes, please. Go straight to the question.
All right. My question is, I think we did a regression, right? So the question I have is, before doing the regression, don't we need to test the stationarity of the variables? Because if the variables go to unity root, our regression results might be spurious. So I don't know if you intend to do that later on, but that is my question. I mean, we don't need to make the stationary test before doing the regression.
Yeah. You know, in the slides, I show you the model selection criteria that we have to follow. And the thing is that let me show you that diagram. For us to use the OLS, our variables have to be integrated at the levels. So I didn't run it because so I presume that the variables are integrated at the levels.
Okay,
you understand?
I see.
I didn't run it,
yes,
so
sir.
I presume that the regressions are stationary at the level. All of them are I0. So if you do the unit root test, I'll later will give you the command for the unit root test. I will give you the command later. If you run the unit root test and they are not all the variables are not integrated at the levels, then you will know which of them that you need to use. You get it? Yeah, but in this case, I just assume that they are integrated at the levels. I assume that just for us to start from somewhere. You get that?
Yes, I got it.
I hope you're okay.
Yes, thank you.
Okay.
Okay, please proceed for us.
Okay, if you are answered, I'm coming. Okay, now let's proceed. Let's move on. The next thing we need to do is that we have to test for. Oh, is it somebody answer? Ask your question, please.
Please, the questions are completed. Please proceed.
Okay, now let's move on. Now let's test for homogeneity of our variance, which is heteroscedasticity. Let's try that. So that one you can type estimate, and this one is, then you type this HETT test. Then you type enter. So you can see that in our case, our model is not suffering from. And the variance in this case, our variance are what? Constant. So it is not suffering from heteroscedasticity in our case because it is not significant. If you look at the p-value, it is not significant. So it doesn't suffer from heterogeneity issue. It doesn't have that issue. Now let's move on. Let's now look at whether we have omitted some relevant variables from our model. Let's try and look at whether we have omitted some relevant variables from our model. So that one you type estimate OV test. OV test. So we are looking at the model specification error. We are looking at that one. So let's look at that. Okay. You're looking at this. So this one, you will notice that it is what? It is significant. The p-value is significant here. So it suggests that it's also here. You can see that the null hypothesis is that we have not omitted any significant, any variable, any relevant variable. That's the null hypothesis. But the p-value here is significant, which suggests that we have omitted some relevant variable. You get it? So when it happens like that, then it means that you have to include other variables to your work because the p-value here is significant. So we have to reject the null here that we didn't omitted any relevant variable. So in this case, all we need to do is that we have to then introduce other variables to our work. So either we drop some of them, then we drop some of our variables and also introduce what? New variables into our model. Okay. Now let's look at the linearity of the relationship between the dependent variable and the independent. They have to be linear. So let's try to look at that one. For that one, we are going to use what we call augmented component plus residual plot to do that. Augmented component plus residual plot. That's what we're going to use to determine whether the relationship that exists between the dependent variable and dependent variable are linear. So let's try that. We type AC, PR, or PR, then plot, and comma, LOWS, okay, enter. Wait. Okay, wait, I'm coming. Let's try this. Okay, let me run the regression. Yeah, let me run a regression and try to look at the linearity of it. Let me run a regression. So I ran a regression. I just ran a regression. Then after that, I type ACPR, then plot. Okay, we do that one. Plots. Then what we do is that, sorry. Come here. Okay. Okay. What we should have done is this. Yes, I missed the code. We have to type our variables. Okay. So let's type our independent variables. So after ACPR plot, the next thing you should do here is that you have to type your independent variables. Okay, so let's try to type that. ACPR plot. ACPR plot. Okay. Then this, we exclude the dependent variable from this. So here we only have the regressors. Then comma. After the comma, then we type LOWSS. Okay, stop. Send that too many variables. Okay, let's try it bit by bit and see. Let's look at how linear with respect to each variable. How linear with respect to, let's do it one by one, so that we can have them. Okay, so we do it step by step by considering each variable, independent variable, and look at how linear it is. Okay, that has come. Okay. So you will see that if you look at the augmented component plus residual plots, you will notice that our model, it is not linear. I see it's clearly deviating from the linear line. So yes, it is not. So it means that our model deviates from the linearity assumption. Our model, this one, it means that you see, look at it. If you look at the graph, it means that the impact of aging population, clearly deviates from the linearity. So the ACPR plots for aging population clearly shows a deviation. So here, the explanation you will give is that you will say that ACPR plot for aging population clearly deviates from the linearity. Okay, it clearly deviates from the linearity. You can see that it doesn't follow that linear line. They should have that linearity then. It doesn't follow it, it deviates from it. So let's try to look for other ones. Like someone told me, I'm keeping it somewhere. Now let's look for others. Let's look for this. So ACPR plots. Then we type the next one. The next variable we are looking at is population density. So LNPGN. Then comma LOWESS and enter. So you can see that, let's look at this one, also the population density, the plot for the population density, let's see, look at it. If you also will notice that even though it's showing a negative relation, the plot indicates a deviation from the linearity, you can see. Because this line, this particular line here, should be on this, should follow that linear line. And it also what deviates from that. Our assumption that our the relationship are linear doesn't hold. So here we assume that the relationship between population density and carbon emission, it is not linear. It's not what linear. You can see that if you look at the graph. Let's test for other things. Let me hide this one too. So I will do for some few ones, then later we'll change the discussion, we'll move on to another thing. Okay, this is the last one I'm doing on this. I don't want to do for all. I think you've gotten the idea. So after this, I will welcome your questions, then we'll move on to another strategy. So let's look at urban population. So we are looking at whether the relation between the dependent variable and independent variable are linear, and whether this is linear. Let's look at that one too. This one is for, so you see, if you look at the population if you look at urban population, okay, if you look at urban population, the relationship is what? Urban population, if you look at it, you can see that it is very linear. You can see that on the graph, you can see that the relationship is what? Very, very linear. So that's this actually meets the assumption, but the other variables doesn't. I think when we go ahead to look the graph for others, we also will notice which of the other variables that their relationship with the carbon emission is linear. Okay, so since I want to teach you another thing, I want us to end here. Then I welcome your questions. Then after that, I will introduce a different method, which will be very easy for us to walk through it. Because once your models suffer from this kind of econometrics problems, then you need to make sure that you go in for appropriate method. Okay, so let's at this point, if you have any question, you can ask.
Okay, so doctor, I'm sure we are a bit tired also, so maybe in the next 10 to 15 minutes, will it be okay to finish?
Oh, yeah, we can finish. I'll teach you two methods. We'll rush through, then later we can have questions. So
okay. So the questions are coming. The first question is from Mama Esther. Please unmute yourself and then ask your question.
Okay, thank you for the opportunity. Abdul, please, can we go to the OLS regression?
He said I should show you the OLS regression. I should show you that.
Yeah.
Okay. I think this is it. This is the OLS regression.
So the GDP, right? The results. You were saying that the assumption is when people income increases, it is expected that they will prefer to live in a greener areas, right?
Yeah, there's a theory like that. There's a theory called Kenneth's curve, which shows that once your incomes are increasing, you want to live in a cleaner environment. And so, you can see that if you look at the developed countries, they rather prefer to invest in the underdeveloping countries. They just move their factories to there and go and pollute the environment because over there the laws don't work. Then they will live in a greener environment. Yeah. Okay, your question.
So assuming that this data is from the developed countries, and then you get these results, it means that that theory is not applicable.
Yeah, it means that no, it means that that theory doesn't hold.
Okay.
In their context. Then you might have to give reasons why it doesn't hold. Because the thing is that for them to create pollution heaven, okay, it means that you, the country, you have a very relaxed laws, environmental laws. So if your laws have your laws in relation to environment is very relaxed, then it means that other foreign companies might want to invest in your country and pollute the environment. So actually, countries with the country with less effective laws, environmental laws, actually attracts FDI that actually pollute the environment. That's what the hypothesis says. So you can then argue from that point.
Okay. Thank you very much.
Okay. Fami, any other question before we move on?
One more question, Doc. So I'm not sure if I can pronounce the name. I've unmuted you. Can you unmute yourself and ask the question?
Okay, hello. How are you? Good?
Good. Please go straight to the question for us.
Yeah, my question is it's not a question, but after the lecture, I would love, please, can you give us the logic of the STATA? Like, at some point, I discovered that in order to make like SCPCT plot lowest, I cannot just choose any random variable. I must choose from the variables that you have made some step before it.
I don't think I got your question right. Can you come again?
Okay, again. Like if you want to make ACPR plot lowest, you can.
The plot.
Refer to the step before that. One of the variables. You
no, you don't. You don't need to.
I don't know exactly.
No, you don't need to do that. You just need to type the command and it will come. But what you need to do is that you have to do it for individual independent variable separately. You have to do it for them separately to look at whether the relationship between the particular independent variable with the dependent variable is linear. That's what you have to do. So what you do is that you first will do a plot for aging population and see whether the age relationship that it has with the carbon emission is linear. So you do them separately. You plot the graph separately. So if you look at this, like, see, this is for that of urban population. So the urban population, the relationship between urban population and carbon, it's linear. So which fulfill the assumption. Which fulfill the assumption that the relationship that might exist between the dependent variable and independent variable should be linear. You get it? So consider this fall on the line.
Okay. I will form my question in a better way. I will send it to the group. Maybe we will have.
Okay.
Okay.
You can get it. You can get back to the group right now. Okay. So.
Okay. Thank you.
We have one more question. Thanks.
Yeah. Doc, I tried to do the same plot in the same way you did, but man, it's not coming up.
What command do you use? ACPR plot.
ACPR plot. Yeah, I use the command.
Then use a particular variable. Like one of the independent variables. Use one. Just type one of them.
I tried using one, and yet it wasn't showing me any result.
Really? Okay. This is what you do. Do is just click on the regression, re-estimate the regression, and do this plot. And let me see. Okay, just do a normal regression. Then just type regress. Okay. Just go to how we estimate the regression result. Click on the regression. How we estimate the regression result. Click on it. Then come back to your command. The command for the plots and see if it will not come.
Okay. I have to get the regression.
Yeah, the regression result. Look at the history bar there.
Yeah, copy the regression.
No, just click on it and type enter. It will do the regression result for you. Then after that,
I have the regression result.
Okay, now you come in with this command, ACPR plot.
ACPR plot.
Then type your variable you want to check whether it is linear.
Okay, let's use the first one, LNA.
GP.
P,
comma,
the
then
LOWESS.
Yeah.
It's not coming up with the graph.
So now you have the graph now.
No, it's not.
Yeah, okay. So now it works. Okay. So that's it.
No,
it's
not.
No,
can I take it
didn't work.
in the? Can I take it in the group? Can he
Okay,
take
I will snap and send to the group. It didn't work.
Yes, please. Snap and take to
really?
the group.
Yeah, it didn't. I will snap and send to the group the results.
Kwame, let's another person try. Let's see.
Yes. So you can continue because it's...
Okay, let's another person try and let's see it. Now let's look at okay, so what it means is that whenever your models have this, it's not able to fulfill these assumptions underlying OLS, then it means you have to actually look for other methods that can account for these errors. That's what you have to understand. So whenever you do your OLS results and it doesn't meet the assumptions, then you have to then look for other estimation strategies that can account for, or that is robust to that particular problem. So first is that one of them is that when let's say when your result is when it suffers from correlation, look at this our model. You can see that when you look at the contingency tests, they are highly correlated. The independent variables are highly correlated among themselves. You understand? So here you can use what we call Twisting regression. Twisting regression. Twisting regression, something like that. I think about this. Twisting regression. I'll just type the command, then I'll do a regression for you. So you can use this one, twisting regression, or you can also use what we call. You can also use similarly unrelated regression. I'm just mentioning them. Just later I will do other estimates. But when you have problems with your OLS, when they are not fulfilling the assumptions, one of the methods you can use is what? Twisting regression. You can use that. Later I'll type one. I'll do a regression of it. Then you can also use similarly unrelated regression. The similar unrelated regression is just a single regression which involves multiple regressions. So in it has a lot of regression. The reason is that those regressors have a correlated errors. Their errors are highly correlated among themselves. So you will have a single regression which contains a multiple regression. That's the similarly unrelated regression. So here you are trying to do estimation to say that those variables are not related to each other. So you can use that method. Similarly, okay, I'm just typing them. I'll use one to do an estimation then. So let's look at the Twisting regression. Twisting regression. The Twisting regression. When you do estimation and your estimation is suffering from auto-regression. I think I've not done for serial correlation. Let me see if I've done for serial correlation. Yeah, I've not done for serial correlation. Let's do for serial correlation. Then after that, it means that the errors of our observation should correlate with other observations errors. So let's look out for the serial correlation. I think I've not done that test. After that, I'll come back to do estimation for that one. Just one of them, then I'll introduce a new method. So let's look at this. You can type estimate estimate B Godfrey or something. B Godfrey, yeah. Come on, black one. Okay. So when you do the estimation, the null hypothesis here is that there's no serial correlation, but you notice that the p-value is significant. So it means that our model also suffer from what? Serial correlation. Suffer from what? Serial correlation. If you look at the test, yeah. The Godfrey test for serial correlation. The p-value here is significant. So we will have to reject the null hypothesis, which suggests that there's no serial correlation, and accept the alternative that there's serial correlation. So here, once this problem exists, we then have to look for other estimation strategies that can understand or that can account for these errors. So I was just mentioning some of them. One of them is the Western regression. Let me do that one. Let me try and do that one. Let's type this. Okay. There is one you type trace PR, trace PRAIS. Then you type the dependent variable like a normal regression, then you continue with the independent variable, then enter. Okay, so this model also helped to resolve the problem of autocorrelation and correlation with your model. The problem of it helps you to resolve that. So you see that Western statistic here, it is less than 1. So it means that this estimation here doesn't suffer from autocorrelation. So you get it. So if your model suffers from this serial correlation, then it is more appropriate for you to use this. Use trace Western regression to help you to resolve that. Then also you can also use this same method when you have a problem of this regression, the problem of heteroscedasticity, or when there's heterogeneity of the variance. When you suffer from that, but in our case, we don't suffer from that, but we can, if that problem exists with our model, then this approach is also robust with that problem. Now let's look at something. You can also use this. You can use the simile unrelated regression. You can use that one also to estimate your model rather than using OLS, which doesn't meet those assumptions. After this, okay, if there's any question, I'm welcoming that. Of course, I don't want to introduce another one. I want to introduce another model. Okay, then if there's no question,
I'm sure our people are tired, but we have 2 people with their hands up, so we quickly take them.
Okay.
Please go straight to your question. Hassan, please, straight to the question.
Okay, let's look at that. Hassan.
Yes, thank you, Doc. With regards the ACPR plot lower, I still can't run it.
ACP?
Yeah, but yes. Doc, I'm coming. Doc,
I've done the regression. I've done the regressions, but it's still not showing the linear. Yes,
really?
The plot.
Okay, let's try this. Try this and see. Which version of STATA are you using?
Sir?
I'm listening. What version of STATA are you using?
18.
STATA, which version?
18.
You are using what? 18. So I think it's
to the group. STATA 18 MP.
And so I don't think you should have a problem with it. Okay, try and do some installation. Let me see. Install.
Doc, a minute. I'm coming. Hassan, the command you posted, I realized you didn't even put a name of a variable. So
you have to add the name of the variable to it. Okay, you have to add.
Yes, I've typed ACPR plot INPODN command, then low.
Yeah.
I've done that.
Okay, can you please send a picture and post in the group so we check it? Because if you post it, I'll be able to see what is wrong. So let's take the next question before we
let's move on. Then the next question before I introduce a new model.
Raphael.
Yeah, anybody? No, there was a lady who has.
My question can wait until the end because it's from far. I asked it in the chat, but I'm assuming Kwame didn't see it. I don't want to take you guys far. So yes. Okay.
Okay, Abdul, you said your Esther. Okay, so let me unmute Abdul. You also said.
Okay, listening.
Hello, Abdul. Please ask your question.
Yeah, my start big of free is not working. I don't know why. It's giving me error. 321 R321.
R
is giving me error when I enter start Godfrey selling R321.
R321. Can you
Yes.
please send a picture? Let's see, because the command here is correct. That's why.
My command is correct.
Yeah. So that's what I'm saying.
So if your command is correct, I think you should
That is
have
the figure.
issues with that. Did you have that?
I've sent the figure. The
Yeah, the command is correct, but it's not.
So what's the problem with that?
I don't know. I have been corrected.
Okay, try and let me see. Try and run a regression and let me see. Run a regression and do that test.
Wait. Check what you wrote.
What's that?
Abdul, kindly check what you typed.
Is it done? If it's done, we can move on.
Okay, let's move on.
Yeah, okay. So the last person is Destiny again. Wow, please go straight to the question.
Okay.
Yes, I just want to answer the previous question on the problem the guy faced. So he just need to rerun the ACPR plot for each variable.
Yeah, you do it for each variable, so it will give you graphs, and if it doesn't follow the linear line, it means that the relationship between that variable and the dependent variable is not linear.
Yes, once he rerun those commands, and then he can do the serial correlation test. It will be fine. There won't be any error, 321 error. So you just need to rerun.
Okay, then get that to the group so that I think he might follow the up. Okay, so like I said, if I first talk about this approach, if your model suffers from autocorrelation, then it's more appropriate that you use the trace wasting regression instead of normal regression. So it means that when even in your work, you can do the regression in your work, but once it suffered from that problem, then you go ahead and run the trace wasting regression as a robust check on your results. You understand it? Because you cannot rely, given the problem, you cannot then rely on the result of OLS. So it's more appropriate that you use an approach that is more robust, or it's robust to that. Now let's look at a different method. I want us to look at this. Okay, I also said you can also use what we call similarly unrelated regression. Similarly unrelated regression. You can use that one if you also face these problems of econometrics problem. So if these assumptions are not met, you can use similarly unrelated regression. Similarly unrelated regression. You just type sure, then sure regress, something like that. Then let me try to get an estimation and see. Okay, so instead of regress, you write SUREG. Then you type your dependent variable, which is carbon emission, then continue with the independent variable. Then enter. So this method is also more robust when you have problem with multicollinearity, you have problem with serial correlation and that stuff. It's more appropriate that you rely on this approach. This is more modified version of OLS. It's just an improved version of OLS. So it combines generalized list method, and also feasible generalized list methods. So you can use this one also. Then let's now look at, there are a lot of methods when you have problems with your diagnostics, you can rely on them. You can either use robust OLS, or you can also rely on weighted OLS. Weighted we have weighted OLS, WLS, something like that. So you can also rely on that one. Now let me look at it. I want to introduce you to this. Let's look at quantile regression. There are two methods I want to introduce you to, then we can call it a day. So we look at quantile regression, then we look at ARDL, because it's very important. Most of you might be using ARDL in your works. We do ARDL and quantile regression. So let's look at quantile regression. Quantile regression. What you should understand here is that an ordinary OLS model just estimates for conventional mean average of the dependent variable. So with the OLS, it just quantify the relationship between the dependent variable and the conventional mean of the dependent variable. So it means that the OLS just look at the average, look at the impact on the average. So it doesn't look at the broad distribution of the dependent variable, the impact that might have the broader distribution of the dependent variable. So we are going to look at quantile regression. This regression actually, it helps us to, it paints a picture for us. It just helps us to look at the impact of the independent variable across different quantiles of the dependent variable. So we look at the impact of the independent variable on the dependent variable across different quantiles. That's what we are going to look at. So first, you can look at the impact at 50% or 25% of the distribution. How would the dependent variable impact 25% of the distribution of the dependent variable? That's what we're going to do. So we're going to look at that. That one is far robust than OLS. It will give you a broader picture. It will give you a holistic understanding of your of the relationship between the variables that you are estimating, because the OLS just give you an average, conventional average mean of the dependent variable. So it means that it's not able to determine the relationship across certain distributions, whether the model is overestimated or underestimated. The OLS is not able to tell you that. So we are going to use a model which will be able to minimize overestimation and also underestimation, because we are going to look at the heterogeneous impact of the dependent variable across different quantiles of the dependent variables. That's what we are going to look at. So let's look at that. This one, what you have to do is that we first have to, if you don't have this, we have to first type this QR. Let's look at this. Type QR, QREG. That's the quantile regression. Then you after that you write the dependent variable, then followed by dependent variable. That order, then comma. After you bring the comma, you write quantile. So quantile, then bracket. So let's look at the impact of the independent variable on the 50% distribution of the dependent variable. So let's look at that. We type 0.5. 0.25, that's 40% of the distribution of the dependent variable. We'll look at that. Then type enter. So, okay, so this is the result when you look at the 55% distribution, quantile distribution of the dependent variable. Look at how the regressors affect 25% of the distribution of the dependent variable. Then we can go ahead to look at 50% of the distribution of the 50% of the distribution of the dependent variable. So what you do is that just click on go to the history and click on it. I just want us to be quick with it. If not, you can just write QRG followed by the dependent variable, then independent variable, then comma. After that, you write quantile, then open a bracket. We've done for 25%. So we can then go ahead and look at 50%, which is the median 50%. So if you look at half of the distribution of the carbon emission, we look at how the independent variables actually affect that part of the carbon emission. So let's look at that one. This 50% result. After that, I'll go through it. I'm just trying to do the estimation for all of the quantiles. And after that, I will explain everything to you. So let's then do estimation for 75%. You see that you can start from 10% to 20% to 30% to 40%. You can do it like that. Per your own, how you want to look at it. Or you can choose 25, 50, 75. It depends on you. So if you want to do a lot of estimation, you can look at 10% of the 10% quantile distribution of the dependent variable and how the independent variable actually influence this portion of the emission. So let's look at this. Let's do for 75 from 50. We'll do for 55 quantile. 75 quantile. So 75 quantile. Just the same thing. You just change the quantile in the brackets instead of the 0.50. We just change it to 0.75. Okay. So this is also the result for the 75 quantile of the distribution. We can stop here, or we can also go ahead to do more higher quantile distribution like 0.90. 0.90. Okay. So that is 90% of the distribution of the independent variable, how the dependent variables are affecting that distribution. Okay. Okay, so in our case, couldn't estimate for the 90, so we just pause at the 75. It's okay, 75. So what you have to do here is that you have to look at the impact of the independent variable across different quantiles, across what? Different quantiles. So let's first look at the impact of aging population at 25% or 0.25 quantile. Let's look at that one. If you look at this 25 or 0.25% quantile, you notice that aging population has a negative impact on carbon emission, but at that quantile, it was also not significant. So it means that when you take 25 quantile distribution of the carbon emission, the aging population has no significant impact on that. So what I will later, when I combine them, I'm just walking you through. Later, I'll let you know what exactly you have to write for explanation. So it means that an increase in aging population has no significant impact in carbon emission at 0.25 quantile. Then let's look at 0.05. At 0.005, you also will notice that it's negative and not significant. I'm just trying to focus on just that particular variable. So we do it in that order. So you can say that one is also negative, but at 0.25, it was not found to be significant. So it has no impact. Look at this one. Let's look at 0.75. At 0.75, aging population is negative, but still has no significant impact at that quantile. So if you look at 0, okay, so I said we should end at this. So let's look at this one. We just focus on 25, 50, and 75 quantile. So you'll notice that the aging population has no significant impact across all the quantile. It has no significant impact across all the quantile. That's the explanation. So you say that an increase in aging population has no significant impact has no significant impact on carbon emission across all the quantiles or across 0.2, 0.25, 0.5, or and 0.75 quantiles. So the same, let's look at that. Let's now focus on population density. With the population density at 0.75, it was negative and significant. So it means that an increase in population density will lead to a decrease, will lead to 15.79% decrease in carbon emission. That's what it means. It means that if population density increased by 1%, it will lead to a decrease in carbon emission by 15.79% across all the quantiles, across 75 quantiles. Let's look at the other quantiles and then we can conclude. So when you are doing the analysis, you have to look at their impact across all the quantiles before you conclude on its impact on the dependent variable. So let's look at that one. You can also see over here it is also negative and significant at 0.5. It was negative and significant at 1%. Then let's look at 0.5. 0.5 population density is negative and also significant. So here you conclude that you're going to say that you found that an increase in population density results in a decrease in carbon emission across all the quantiles. If you like, you can explain it given particular quantile. You can talk about individual quantiles, then they are at the individual quantiles and the impact. So it was found that an increase in a 1% increase in population density will lead to 11.58% decrease in carbon emission at 0.9 quantile. You can do that. You can look at it from separate quantile, or you just match them. So they had a negative impact across all the quantile or in all the quantiles. So now let's move on. The next thing we'll do is,
Hello, Doug.
Yeah.
Hello, Doug. I think we've gone into like 4 hours now. So you are closing us anytime.
Is that?
Yeah, you are coming next week for panel data. So maybe you may start with the next models, if that's okay.
Oh, it's left with some few this thing, then I'm done. Then I think because if I'm with the panel will be a different model. So this time series, okay. Let me finish up with this, then later I'll continue.
Okay.
Now let's move on. Let's now look at the graphical of the results. How can you represent these quantiles on a graph? How can you do that? So if you don't have this quantile plot installed on your STATA, you just type SC install. Then you type GR, then QRG. Then you install that on your STATA. Okay, mine is already restored, so I've already installed that on my list. But those of you who don't have, you should do this. SSC install GR, then QREG. You install that on your in your STATA, and then we can go ahead. So now let's look at something. Let's write this. After you've done that, you write. It's what you write. Okay. You write this, quietly. Okay. you write quietly. Have you seen that? You write quietly regress. Quietly. I think I didn't get that. Quietly regress, not QR. Just regress. Then you regress in this case, we're just running a normal OLS model. So quietly regress. Then after that, write the dependent variable, then independent variable. That's enter. So that's recall just recall the OLS results. Then after that, you can type estimate HETTES. So we want to look at the homogeneity of the variance test. We want to look at that. So after that, that's what the next thing we need to look at. So let's type this with the dependent variable. We want to look at whether the impact of the independent variable is heterogeneous across all the quantile. That's what we want to look at. So you type estimate, then estimate and HETTST. Then after that, just follow up with the independent variables. In our case, you type, I don't want us to delay, so let me find a easy way to do that. Okay. So after that, we have to type IDD, meaning it is identical. The errors from these variables are identical and independently distributed. And type. Sorry. I think it has gone to. I don't need to include the dependent variable. So take out the dependent variable. Okay. So you notice that the p-value is not significant. So what it means is that our result, our quantile regression result is homogeneous. It's not different from the result of the OLS. That's what it means. So it means that the impact of this variable across the quantile is homogeneous. Now let's look at this. Let's try to do a graph to look at what will happen. Let's look at a graph. So let's type quietly, then you type QR, then then you type carbon emission, then follow up with the independent variables, then enter. So we record the quantile regression result. After that, you type graph QRG, constant, that's the intercept, then OLS, then you type confidence interval. After that, OLS, confidence interval, enter. Okay, so let's wait for the graph. I will use the graph for the explanation too. So let's wait for the graph. The graph is taking time. Still don't have the graph yet. Okay, let's wait and see. I don't know why it's taking some time. Try maybe to show. Not yet. Our graph is not yet. Okay. Let me run it again and see. Press quietly. Then graph the OLS and let's see. Let's wait for the graph. Okay, now we have it. Okay, so if you look at the graph, if you look at this graph here, you see some dot lines. See the small dot line. One is up here, another is up down here. That is the confidence interval. So this one is the upper and the lower confidence interval. The dots, the small dots you see up in the graph, the small one is the confidence interval of the OLS result. That's what you have to understand. Then the big one, see the large dot, which is very horizontal, the large one, the large horizontal black dots. See, that one is the coefficient of the regression across. That one is the coefficient of regression. It's very constant. I told you that with that one, there's homogeneity of the variance, so it's very constant. Now, what you're seeing here, the line is the quantile plot. That's the quantile plot. So the quantile plot here fall within the confidence interval of the OLS. So it means that the results, it means that the results that the result of the quantile regression is not different from that of the OLS. But here, when you are explaining, you are going to say that the impact of the independent variable does not vary across the quantile. Does not what? Varied across the quantile. In effect, you are trying to say that there's an homogeneous impact of the independent variable across the quantile, because you can see that the plots fall in between the confidence interval of the OLS. When it is outside the confidence interval, okay, when the quantile regression, the quantile plots, when the quantile plots line there, if you see it to be outside the confidence interval, then it means that the impacts of the covariances varied across the impact of the covariances on the independent variable, in this case, the carbon emission, varies across the different quantile. But in our case, we notice that they fall within the confidence interval. So once they fall within the confidence interval, it means that it has homogeneous, the covariance has homogeneous impact on the carbon emission across all the quantile. The same when you come to aging population, you can see that it also falls within the confidence interval of the OLS. So it means that there's an homogeneous impact of the independent variable it means that the aging population has an homogeneous impact on the carbon emission across all the quantile. So here you can see 0.2 point. These are different quantiles. So this one is 0.20, 0.40, 0.60. These are all quantiles. So it means that across these quantiles, the quantile distribution of the independent variable, the impacts of aging population is the same, is homogeneous across that. That's what it means. The impact, it doesn't have heterogeneous impacts. It doesn't have on the carbon emission. So you have to observe that you consider all our variables have homogeneous impacts on carbon emission. If you look at it, because they fall within the confidence interval. That's what so you have to understand that whenever the quantile plot is outside the confidence interval of the OLS, then you can conclude that that particular variable has heterogeneous impact on the dependent variable across different quantile. Anyway, at this point, we'll end here. I think because I'll be taking you guys. I'll be the one to handle the panel data analysis. Before we do the panel data analysis, I'll chip in ARDM model for time series. We just use a few minutes to do that. In our next meeting, before we then go ahead to do the panel data analysis next week when we meet. So we'll end here, and I want to welcome your questions.
Thank you so much, Doctor. 3 good hours. Wow, that's a lot. And hello, fellow colleagues. We do apologize for the time, but trust me, this content is way, 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 way deep, and I think these are something that might take you years to learn. So we have to take our time, revisit the video. Doctor, please, can you send me the do file together, all the things we've done, without even deleting the errors, like just everything, and then the PPT, so I can share with my people. Is that okay?
I should have saved it. Anyway, I'll try and save it, but I think with that one, you might have, I should have saved it from the initial stage because I didn't do, I didn't set the do file. Anyway, I will try and save it. I will send you this. And I'll send you this and the PPT.
Yeah, I think from here, what we have is okay. What we have is okay.
Oh, okay.
Okay, thank you so much. And I'm not sure, we will not have the Q&A. We can't have the Q&A after the meeting. So we will see you next week. But I think, Sam, you have a question. Just one question and then we wrap up. Just one.
Okay, when you have a question, we can.
One person has a question, so just him and then we just wrap up.
Okay, Doc, thank you so much for your time. And please, I want to ask this question because some of us who are under education, mostly sometimes when we do our research on primary data, we going to use this STATA
this approach is also applicable to primary data. You can use quantile regression for primary data.
Okay.
So what you do is that when you are doing the quantile regression for primary data, you can use this one. You can use OLS and also use this quantile regression. After you have used the OLS, you later will use the quantile regression.
Okay. So that's basically my question. Thank you so much.
Thank you. I think we will have the primary data session next 2 weeks. Next 2 weeks.
Is it next 2 weeks? It's next week.
Yeah, next 2 weeks. Dr. Toba will take us through the primary data analysis. So yes.
Okay, they'll be doing primary.
Yes, sir. Abdul, you have a question, but we are closing, so let it be very quick, please. Very quick.
Okay.
Hello, Abdul. Okay, so we continue on. I think he's not talking. So we just continue.
Okay, then we.
Okay, so Doc, on behalf of my people, we say a big thank you for the 3-hour marathon and then the time you've taken to impact us. We really appreciate it. And so the request for your WeChat, please give us your word before we close.
Or you can give it to them. There's no problem.
Okay, thank you so much. So I'll share it. And please send us the do file and the PPT so I will share with my people. Okay, so fellow colleagues, thank you so much for joining us. Some of you have been here for 4 hours. Some of you have been here for 3 hours. Thank you so much for being here. And we apologize for the time, but trust me, just spend 20 minutes a day going through the things we learned today, and you have about 6 to 7 models to handle your time series data. May God bless you for being here. Well, let me take the opportunity to introduce you to OAAD, which is Association for African Academic Doctors. If you are not in their group, please join, and the benefit is endless. With this said, thank you, and we'll continue the discussion in the group. You can post in your questions, you can bring your suggestions, and I also apologize for muting all of you because I needed to. So next week, we hope it will be much more better. Have a great evening and see you next week. Okay, so Doc, please, the DOFA, we really need a DOFA. So please help us.
I'll do that. I'll try that. I'll try and get you that.
Okay. So